Stage is yours.
Wonderful. Thank you very much. First, a disclaimer. They are building downstairs. I went there and said, like, please don't build anything during this time of the talk. But if they do, then I'll run down and shout at them. Great. We're coming now to, talk on quantum machine learning, which builds very much on the ideas and structures that we heard in the previous talk. And just a little bit of preparation. I will not talk about the full depth and breadth of quantum machine learning here. There's a lot of topics that have nothing to do with what I'm talking about. So this is more focused on near-term computing. This is more focused on basically making quantum computers trainable and using them as part of big machine learning pipelines. And as Christina said, like, there's a lot of connections actually to quantum control. And I think we haven't even started to uncover them. Just two anecdotes from my side. So first of all, I was a year ago or two, I was I was speaking at some kind of like conference or little workshop at UCLA, and there was like a talk about quantum control, and I sat in there and just thought about machine learning all the time. They were talking about uncovering these like valleys in optimization landscapes and quantum control being like, robust against lots of things. And I just thought this is like machine learning to me. And the second one is that actually a lot of what has enabled this type of machine learning that I will talk about is what we think of as quantum differentiable programming, which means we can compute gradients of quantum computations and we can start optimizing quantum computations. And it was very much initiated after a little bit of history of like people looking around by a paper that took the initial concepts from quantum control. So there's a lot, I think, that can be discovered, and I hope maybe one of you will be the person who actually gives this input to quantum machine learning. Setting the stage. So there are lots of ways to combine quantum computing and machine learning, and you often see this picture in talks on quantum machine learning that's distinguish the type of data that you use. So is it produced by a quantum system in some way? Is it even quantum information itself? Or is it like normal classical data, like in any machine learning problem? And what algorithm or what computer do you use? And I will only talk about having classical data and using a quantum computer. So what can quantum computers do basically to enhance classical machine learning as people know it for centuries? Well, 1 century probably. And then secondly, I just mentioned already, there are very different ways to think about quantum machine learning, depending on if you think of good old quantum computing in a type of like speeding up algorithms, like using, for example, routines that have been discovered to speed up matrix inversion. Maybe we can use this in machine learning and so on and so forth. Or if you think of near-term quantum computing, because the requirements are different, the communities are different, the way what is considered to be a good outcome is very different. So I'll be in this part, as I said. And everything I want to say is basically on this slide. So I take a bit of time to go through here, and then the rest of the lecture will just be, like telling the story with a few more words. And you don't need to know how to code in order to read this. So just think of this as a picture. What you see on the left side here is a machine learning program, a very stupid one, a very simple one, written in Torch. You see here, maybe if you've ever done machine learning, you see the important elements, which is like data, you've got a model, and then you define some loss or cost function, and then the rest of it is just an optimizer. And so machine learning, just as a background, or modern day machine learning, this is why I talk about differentiable programming being so important. It's basically just an idea of having a model or computation that depends on parameters, and then having very elaborate methods to find or to optimize this model given some data. On the right side here, you see basically a similar coding example, but this time it's a quantum machine learning example. And I thought, so basically it's written in PennyLane, first of all. PennyLane is a software framework. Let me just show here that Xanadu and the team that I'm at Xanadu is very involved in like developing. And it's a quantum computational software framework based on quantum machine learning, all these ideas that are present here. So a lot of what I say, you can, if you're like coding, you can actually look onto these homepages. This is pennylane.ai. I think I have a link later, and you can find a lot of examples and tutorials. Getting back to here, why this is so nice is you can see the code is exactly the same. So the pipeline of optimization, defining loss, defining data is exactly the same in this way of thinking about quantum machine learning. The only thing we replace is the model. So basically we say, instead of a model like a neural network, you might have heard of those, or support vector machine, or whatever you use in your machine learning pipeline, we use a quantum computation. And there are two important questions. The one is probably more important for the quantum control community, so I'll talk about that first, and then if I've got time, I'll talk a bit about the second one. The first question is, how do we optimize? How do we train these models? And and we will see that it's possible to train these models. So the question basically is, if I interpret a quantum computation as a model and I want to like optimize it, how do I define gradients of that model? So that I can actually add it to this machine learning pipeline as Penny Lane does it. And then the second question is, that's a bit more like the machine learning side of things, not so much the practical implementation. And this is, what does this quantum model actually, what does it look like? Is it a type of neural network? Is it something completely different? And I hope I give you some answers if I get to that part. Okay, great. So before I start, I know that not everyone in the audience knows about machine learning, and usually people always introduce it like saying this is a neural network and it distinguishes between cats and dogs and deep learning is really great. But since this is probably an academic audience, I want to summarize what do we actually try to do in machine learning, and what I want to work out is where does optimization come in, because this is like interesting for you guys. So again, there are basically three ingredients to machine learning. Here I'm dumbing down machine learning to like the problem of supervised learning in a very like typical setting. So you've got data, and in supervised learning, which is the setting that's probably the most well studied, you've got your data is given by inputs and outputs. And the question, or it's very unclear what actually produced this inputs and outputs. For example, your data can be images and your output could be what's on the image. Is it a cat or a dog? And then you don't know what mechanism is really there, or what algorithm to really program to just define what on the picture is now a cat or a dog. So first ingredient is data. Was this line in the little example. Now the second ingredient, and this is the one that we want to replace with a quantum computation, is a model. And the model basically is the map from inputs to outputs. And very often, not always in machine learning, models depend on parameters. So when you define a model, you actually define a model family. For example, a family of linear functions in this case here in the picture, or step functions in the other picture. Let's leave it there. This was the second little ingredient. And the third ingredient is you have to define a loss. A loss basically, in the most granular part, is a comparison between what the model predicts should be the output and what the real output was in your training data. And this loss function is now defined, for each data point. And then in the end, what we want to do in machine learning, and this is kind of, here's the code for this. This is the big problem, is we want to minimize the average loss of the model. So we want to find the model in the model family for which the average or expected loss over all the data we could possibly encounter is minimized. And this is the optimization problem we have in machine learning. So now here's a problem, obviously. So just to explain here, on the x-axis is basically like the model family plotted. So every of these points is a model of the family, and we try to find the best one. Now you could say, okay, let's just optimize this. But obviously, what I just said, this is the expected loss, so the quality of a model measured on all possible data. And as you can imagine, it's never ever possible to have all data. I mean, this is quickly very intractable. To even define the space of all data is quite fuzzy in this sense. What you have in machine learning is a different optimization problem. You've got an empirical loss. You've got a couple of data points that are samples of this class of data. You hope that these data points you've got are a very good representative of that data class you want to learn. You've got a proxy function, basically, you can optimize. And so here is now the big point why machine learning is not just optimization. Machine learning is basically optimizing this proxy function in order to optimize a function that I don't have access to. And you might know this kind of concept of overfitting already from your physics undergrad or something. The danger here, and what you want to avoid, is find solutions in your green function that you have access to that are like this. These are functions that totally overfit your data, but if you add new points, they would not generalize. And you can see this here because it is actually not a minimum of the black function that you really want to minimize. People in the last 100 years have thought about a lot of solutions, or it was like dominant theory to find these types of solutions here, where you kind of don't really have a very low minimum of your green curve, or your empirical loss that you can optimize. because you don't hit all the data points in some sense, you don't fit it very well. But people thought that you're probably also guaranteed that your real function that you want to optimize is not doing too bad either. And now, just a very quick note on deep learning. So a big revolution in machine learning very recently is this idea, or are these models that are called deep neural networks that, together with optimization strategies and certain types of data, find these solutions here, where you go actually your empirical loss is really, really low, and your generalization is also very good. This just like as a side note. Okay. And this is now the whole pipeline, and a lot of work in machine learning or fantastic algorithms have been developed to do this optimization. So lots of people do stochastic gradient descent type algorithms with lots of variations. Computational power is used in crazy ways. So there's actually a lot of convenience structures to optimize things in machine learning. So machine learning is in some sense today more than just learning or statistics. It is actually differentiable programming, that you can optimize big programs that are the models in machine learning. Now, what happens if we interpret quantum computations as models? I'm not too sure if all of you really know what a quantum computation is, but after the talk beforehand, you probably do. What I just need here, or what I define as a quantum computation, is the following. We've got, physical systems of n subsystems. Sorry, a physical quantum system of n subsystems described by a quantum state. And then obviously most of you know that any evolution, so also like a quantum computation, is kind of just this unitary transformation of this input, which gives you like another quantum state. And now quantum computers generally always measure, as you know, any quantum quantum theory is basically a theory about measurement statistics. But what I want to define as a quantum computation here is the process of measuring and averaging, which is basically to compute expectation values. So this is quite important because if we define gradients of quantum models, whatever they are, and we have kind of a probabilistic outcome, it starts getting very fuzzy what actually the gradient is. So for me, a quantum computation is always an expectation value of a measurement observable. And as you all know, you get them through this like quadratic form here of sandwiching a measurement operator with like the quantum state. As you also know from the talk previously, our quantum circuits are never like a big unitary. There's just a mathematical abstraction, but there are local unitaries, like so there are kind of chains of these operations. I need this a bit later as a fact. And then I think in the quantum control community, I don't have to tell you, although for quantum computing, this is quite a new way of thinking about quantum circuits, that all of these unitaries here, all of these quantum gates can be, or in general, they are generated by some kind of physical parameters. If you've got a fixed gate, like a C0 gate, you have to like find the evolution that actually fixes these physical parameters to generate that gate. But actually, you could also give us as quantum programmers access to your physical parameters, whatever your system is. And then we have parametrized unitaries here. And as you can imagine, this is quite interesting for machine learning. And what you do since centuries, and what we in quantum machine learning only do since a couple of years, is now to think of how can you optimize these parameters of the quantum circuit to train a quantum computation as if it was a machine learning model. One last ingredient that is important here, that I'm totally obsessed with this idea, and it's, I think, the most central part of quantum machine learning, which is how do you encode your data? I mean, in a quantum algorithm, an algorithm is always an input mapping from an input to an output. And in the machine learning sense, this input is data. And the part of a quantum circuit that encodes the data, what it actually does in terms of maths is it parametrizes another unitary that you use for state preparation with your data, and maps the data to a quantum state. So basically, it is a map from data to a high-dimensional state that lives in a quantum Hilbert space. This is the second thing that becomes important when we think about machine learning. Okay, and so these ingredients is put together, now build our quantum model. I've got some data, classical inputs, I encode them in a quantum computer, I do some processing that's trainable in some sense, then I measure, and then I get an output. Let me check the time. Okay. So, and now there's the question how to train these quantum models. And this is this kind of insight that came actually from quantum control theory. The setting that I want to describe here is a slightly bit larger than what I was talking about only in terms of like a single quantum computation. Imagine you've got a huge computational graph. So a huge hybrid computation where basically parts of your algorithm of your computer program are classical and parts of them are quantum. We call these like nodes. And the results of one feed into the other. Why we're thinking of this is because this is how you usually think of a machine learning problem. It's basically just different parts that are modular. For example, a neural network, then a cost function, like a neural network with different like modular structures inside it. So machine learning is kind of this huge modular computational graph. What happens now if some of the nodes are, quantum computations? The whole computation in the end leads to a cost function that a machine learning will want to optimize. This is this loss data set that we have to like find or optimize to get the best model in the end. Okay, and how do we model our quantum nodes? It's also just repetition. So the quantum node, in some sense, just sends a bunch of parameters. These could be data points. They could be trainable parameters. Whatever like kind of defines this computation. It sends it to the quantum computer that sits somewhere on the server, like or in Yorktown or wherever you want to have your quantum computer. And then in the end, the quantum computation sends back expectation values, the results of your quantum computation. Okay, and now the question is, if now some of your gates, for example, depend on a parameter mu, and to optimize the cost with a gradient-based method, I want to find the partial derivative of this expectation value with respect to mu. So this is the idea of like kind of getting derivatives of my quantum nodes, partial derivatives, in order to do like my stochastic gradient descent algorithms. And how can we do this, or what is the problem in the first place? The problem in the first place is that the partial derivative of an expectation value with respect to a control parameter might actually not be a circuit or an expectation value, a quantum expectation value itself. So we might not be able to get it out of a quantum computer. And if we can't get this value out of a quantum computer, we can't simulate it classically either. And so it turns out, and this is like kind of, so from especially this paper here has really popularized it, that for many quantum gates that we're interested in quantum computations, for example, these Pauli rotations we heard about earlier, for many of those gates, we can define so-called parameter shift rules. In the case of Pauli gates, it is a rule of 2 terms. And what are these parameter shift rules? They mean that you, so to get the gradient or the partial derivative of an expectation value with respect to one of the parameters of your gates, you just have to run the quantum computation twice. Once, you use all the original parameters, except from the one that you want to get the derivative of, and you shift it to the right, and then you run the computation again, shifting it to the left. And this looks very much like a finite difference rule. So, like you wiggle a bit to the right, you wiggle a bit to the left, and you approximate your gradient. But in this case, it's not an approximate gradient. This gives you the analytic gradient. So the shape of quantum mechanics basically allows you to run 2 quantum computations to get information on the partial derivative of your results with respect to circuit parameters. I'm not entirely sure if this is very known or widely used in control theory, but for us this was mind-blowing. And in the end, for example, the framework of Penny Lane is really built on this rule. So what it does, and the program that you saw earlier, is basically just it uses pipelines built in machine learning language, like PyTorch TensorFlow. You just saw like a PyTorch pipeline, or also just in normal like standard Python NumPy. And these pipelines will either ask for the output, the forward pass, the prediction of the quantum model. So Penny Lane will send it to the backend, which could be a Qiskit backend or like whatever computer you want to plug in at the back. And Penny Lane forwards it, or the framework asks for gradient information, and then Penny Lane just knows what parameter shift rules to apply and runs them on the quantum computers and passes them back. So it's basically a management system. And a lot of the other quantum machine learning frameworks that work in this sphere are also just like management systems of gradients in some sense. So this is why this is so explosive for us. There are a lot of questions that we have that might have answer in the control community or not, which is, for example, how can you speed up this computation so that you don't, for every single parameter that you have here, you have to have 2 circuit evaluations. So in classical machine learning, you can actually save a lot of steps by sharing information on partial gradients, so which is called like back propagation in the training of neural network. We can't really do this because of how quantum theory is structured. So there's a lot of like ideas that we're trying to like optimize these kind of processes at the moment. There's also a lot of optimises people have come up with, and it's actually quite beautiful because quantum computing sometimes gives you slightly different ideas on things. For example, to make, if you know what stochastic gradient descent is like doing gradient descent where each optimization step looks at all the data you have, but just a little bit of the data. And in quantum computing, you can do double stochastic gradient descent, where you also only do very, very few measurements on very few data points. So you can play a lot of games here that are quite interesting. And already in the previous talk, it was mentioned that we also have a big enemy, so to speak, because theoretically, and for circuits that are kind of theoretical constructs, but seem to also be represented by the circuits we are interested in to a certain extent, you can show that gradients of quantum circuits vanish on average. So if you just like initialize your parameters randomly, you will see that the gradient at that point is very likely to be almost zero, which means I can't really train. And so this is a huge research field at the moment, how to avoid those, in what context they appear. For example, do they appear on photonic setups as well, if you have continuous variable quantum computing, or what can I do to initialize my parameters, and so on and so forth. And then lastly, but here I can talk about this probably for a whole day, but I'll just do like maybe give you a 10-minute insight on ideas in quantum machine learning that ask actually what are these quantum models, because I think especially in quantum computing and especially in industry, we're very tempted to always think only because something is quantum, it's immediately better, because we're so schooled in thinking of better as asymptotic speedups. So we know quantum computers are asymptotically better than classical computers. So they have to be immediately better at machine learning. And this is definitely absolutely not true. You can build a quantum machine learning model that's extremely stupid, and it's very hard to compete with something that has been developed over 100 years, like neural networks. So we have to start really understanding what are these quantum models. And obviously, where we're taking our cues off is like classical machine learning. Now, I know that not all of you, nowadays you can probably hardly do science anymore without hearing about neural networks, but not all of you really have like sat down and understood them. But I just want to make a couple of comparisons to neural networks for which I only need basically you to know the mathematical structure with this like picture language I had earlier. A neural network, when you see like it pictured as this, basically means the following. You take an input, we think of this as a multidimensional vector, and you multiply it with a matrix of weights that you can train. And then you do a nonlinear operation on any element of the vector that is the result of this matrix vector multiplication. And you chain this operation. So you do this over and over again. So this is what's referred to as depth in deep learning. And in the end, for example, you could have a row vector of the same dimension as your final output here, and then you get a scalar output, for example. The scalar output is signified by this one neural unit. So basically, neural networks, for example, the most popular method nowadays are like concatenations of linear transformations that are trainable and nonlinear operations. And now, a lot of times you hear that, so the word quantum neural network has millions of meanings, and every paper that you read probably has a completely different idea. But you increasingly hear this term for these variational quantum circuits, these trainable quantum circuits that I was talking about and also you heard about in the previous talk. I'm personally not such a fan of this, name because of the following idea. So in some sense, there is a similarity. If you have a quantum circuit with different gates, we now just don't think about the measurement for a second. Basically, what you do, you encode your data somehow. Afterwards, you've got a quantum state that represents your data in some way or the other. And now you just do these like unitary, which is also linear transforms. And these transforms, as we say, are trainable. So in some sense, a quantum circuit is a neural network whose weight matrices are unitary and that doesn't have these nonlinear operations in between. So why am I not such a fan of this comparison then? These nonlinear operations are what make neural networks really powerful. So the whole power of machine learning is sitting in them. And if a quantum circuit basically just implements linear transformation after linear transformation, what we get is a really hard, deep optimization problem without the benefits of the nonlinearities. There are lots of papers that think about how to put in nonlinearities here, but they're all very unnatural. They're all like use measurement and post-selection and like routines that are, I don't know. They are just not very generic for quantum computing. You can play games of like starting to think if this is like kind of a weight matrix of a neural network, and a neural network can be seen as this connectivity structure that comes basically from biological neural networks like those in our brain. what neural network structure do quantum gates have? And you can see that they're actually very, if like the same colors here are like the same values of connectivity, like the quantum neural networks, if you want so, are basically not only linear neural networks in a very high dimensional space, but they also have a very, very symmetric weight structure. So there's interesting stuff to really start studying here. What I'm really, really interested in, and I love this topic, is that quantum circuits can be much more interpreted as a different machine learning method that if you're not into machine learning, you probably have never heard of it because it was very popular, as popular as neural networks, but in the 90s, and now neural networks have like kind of taken over. And they are so-called kernel methods. They're quite tough to explain, but if you do quantum mechanics, you probably get into it very easily. So let me just give you a vague idea. Let's say you've got data in this kind of input space. Typically, how you introduce kernel methods is with a very specific idea, which is a support vector machine, which is a machine learning model. And the idea of a support vector machine is that you define your model, your f of x, as mapping your data inputs into a very high dimensional Hilbert space, usually, and taking inner products of some trainable, like other state with your high dimensional representation of your data. Very often in these methods, you go to infinite dimensional spaces. Now you will ask, how can a computer compute in an infinite dimensional space? And it turns out, and that's the beauty of it, basically, that you never have to really like compute these objects here. You can just take inner products between the feature representations of data points themselves. Also, this is obviously an intractable computation, but it turns out that a lot of these inner products you can actually represent very efficiently, or let's call it the other way around. You only consider models for which basically these inner products are functions that are very easy to compute. For example, a Gaussian of the difference of x and x dash. That could be a function that you can prove a feature representation of this form that is an infinite dimensional Hilbert space. You will immediately see why I'm so excited about this, because this is, for me, pure quantum mechanics, right? I told you before that what we do in a quantum computer, we map data to quantum states, which are states in high dimensional, sometimes infinite dimensional Hilbert spaces. And then you know quite well probably that you can take easily like inner products or compute overlaps of these quantum states. Or, for example, train another state and then basically just take the inner product of this one. In some sense, any quantum computation you actually do does this, because you kind of like map your data into a quantum state, and then you start like learning. If you have a variation circuit, you start like learning the second part of the quantum computation, and this in some sense learns a measurement that has exactly this outcome. This was a bit confusing, sorry. Let me try to say this in maths. So basically, when you map your data into a quantum computer by encoding it in the first step, and now this is kind of the output of your quantum algorithm, because you basically just you change your measurement basis and then you measure. So this is represented by this M operator. You could think of a measurement as the outer product of two quantum states. So you just measure the overlap with this quantum state W. And if you write this, you get exactly this form. And this is what I showed you like earlier, why I'm so excited about it, because this looks exactly like kind of this model here, except from that it has like an absolute square and, works in kind of some kind of complex valued Hilbert space, which is at the moment giving me quite a lot of headache, because this is a subtlety that introduces a lot of complexity in the theory of kernel methods, but it's, you see that it's immediately very similar. And lastly, just to say, like now the crux, if you think about it this way, the crux of the method, let me just skip a bit earlier, sorry, just skip back to this one here. You could think of now doing quantum computation for machine learning in two different ways. You could think of, as we do it normally, you just train some kind of like overlap state and then take overlaps, and this is your model. This is basically what we do all the time, just mathematically interpret it in a different way. Or you could compute inner products of quantum states and put this into like a classical machine learning method. But the entire power of your quantum algorithm is now in what is this red feature map here? How do you map your data? Do you separate it nicely? So can we in some sense like map data into like a quantum, so this is like a cartoon of a blosphere, into quantum states that are already separated in the classes of the pictures, for example, they represent, and measurements then just distinguish between the two. So the idea is, what is a good quantum feature map? I will actually jump over this so you can go through a couple of examples. Basically, just any circuit could be a quantum feature map, like a map of data to a quantum state. And the way you kind of like can study this is now as follows. First of all, 1 second, sorry, like I scrambled my slides a little bit, and now like I'm back on to. The second part before I come to that is we can actually train our feature maps. So if you interpret a quantum circuit that encodes data as basically this like map to a feature space, you can actually put trainable gates into that circuit, and you can start like playing around with training your embedding, which is something that is not supernatural for classical kernel method, but in some sense it combines the ideas of neural networks that are trainable and modular with kernel methods that do these like feature maps. So this is like something that's extremely interesting. This one. And then very lastly, and this is already a bit of an advanced topic, so this is why I keep it for the last minute. But I want to pitch it in some sense because this is something that I'm really interested at the moment about. And I don't know how much it is actually known in quantum control. Probably it's very known, and if so, then I want to hear about it. If you think of a quantum model or quantum circuit, which in my language now is the same thing, that kind of has a structure like this. It does something. So these purple blocks are always like do some arbitrary unitary transformation, and then encode some input data, then do another arbitrary unitary transformation, encode your input data, and so on and so forth. These green blocks are always the same thing. One can show quite easily that you can write the result of this model as a Fourier series or a sum of like, Fourier type basis functions, where the Fourier coefficients are basically influenced by these like purple blocks and by what you measure, and also to some extent by the green blocks. But the important thing is that the Fourier frequencies are only defined by basically how you encode your data. To go a bit more into detail, if you encode your data in these circuit blocks by gates that have the structure here, then it depends on the spectrum of this Hamiltonian, which is kind of the generator of the encoding. And you can actually like play this game in practice and see that this is happening. So for example, what I'm trying in this little experiment, this is done with Penny Lane, I'm trying to fit a ground truth function that is a Fourier series of degree 5. And you can now kind of take a quantum circuit, like a quantum model, and start to optimize it to fit this function. So we're not doing machine learning here, really. We're just like trying to fit a function from data points of this ground truth. And this is, for example, the circuit where you do anything. You encode your input in a Pauli X rotation, which has exactly this form, where H is like Pauli matrices. And then you just do something arbitrary again. And you can see what you see here are already trained quantum circuits. The quantum circuit can never be trained to anything as high degree as the ground truth if you only have one encoding. It turns out that if you repeat your encoding, for example, sequentially or in parallel, you can start fitting higher and higher order Fourier series. And finally, and this is quite nice because a Fourier series of degree 5, if you use this Pauli encoding, so it's not true for every quantum circuit, but for this particular one, which is a very typical one, if you exactly repeat your encoding 5 times, either in series or in parallel, you can actually fit this function very well. A quick note of this, so this we kind of worked on this for a long time and thought about it in the context of expressivity and put out this paper, and then a week after it came out, we realized that actually the other authors have published the same mathematical operators with these Fourier series a year earlier. We still have to like update like a new version where we acknowledge that. But so this paper here is the one that actually noticed this Fourier idea first, and now here it's kind of used to understand or make assumptions on machine learning. Okay, cool. So why I'm actually mentioning this is that if quantum models and quantum circuits have this Fourier structure in the data, you could replace data by tunable parameters. So your tunable parameters also enter in this type of way. So that means we also have a Fourier structure in the tunable parameters. This tells us immediately something about our optimization landscape. This tells us about which models we can fit. This tells us how smooth the functions are that we can learn. So a lot of, like a whole universe like opens up from this formalism. Okay. That's it. So as a summary, machine learning is often basically just a mix of different things, of somehow data, models, and then optimization algorithms. I've spoken about replacing these models with quantum computations. And when you ask, like, are now quantum computers better at machine learning, which is like a question I always get asked, especially when people are not coming from quantum computing, so they don't know like how complicated this question actually is. then my answer will be we really only started to explore the properties of these models now. And one has to be very careful, and I hope my introduction on machine learning showed that we don't only try to speed things up or solve optimization problems. We want to come up with models that actually have a better generalization power, that optimize this green curve you saw, but actually find very good solutions for the black curve, which means that the models generalize well. So this is a big challenge to study, to investigate, to benchmark. Some of the things really we have to develop even new methods to even start understanding this. So I leave you with a lot of open questions rather than any answer to this problem. And I would be super happy if so the quantum control community would really come on board to help us to solve a couple of problems we have with optimization, to share what they know about the landscape of optimization of quantum circuits. And we could probably really do a big jump with this knowledge that hasn't been tapped into as far as I'm concerned. Great. Thank you very much.
Thanks very much, Maria. Thanks also for perfectly staying on time. And we have Alistair again for the first question. Alistair, please.
Hi, can you hear me?
Yes.
Awesome. I was wondering, when you're doing this, I think, parameter shift method to determine the gradient of the quantum circuit, how fast do you need the computation to be, the quantum computation? If I wanted to do a closed loop optimization of some sort of experiment, how many, or I guess it depends on how many steps you need to take in the gradient descent, but do you have a feeling for how fast the computation has to be to make it tractable?
So it's definitely tractable. So because if you've got, let's say you want to optimize 100 parameters, you just have to basically evaluate 200 circuits. Obviously, every circuit, no, that's actually imprecise, because when I say evaluate circuits, I mean run the circuit a lot of time to estimate the output, right? So for every parameter, we need 2 estimations. Every estimation has a lot of shots to estimate an expectation value. So it's totally tractable. But as you say, there's a lot of small print here. So for example, as you say, so a lot of frameworks nowadays, for example, Penny Lane would create a parameter shift rule and would then send jobs to for example, IBM Quantum Experience or something, or chips that are somewhere in the world. And you're right, if you then wait in the queue and get your result only back after a couple of seconds, and you have to do that for 1 million parameters twice, even if the shots are executed very, very fast, you very quickly run into problems. So at the moment, all the, I think, hardware and software companies are very mindful of optimizing how they send jobs in batches, how they, how these queues work, to actually consider that. Classical machine learning is only possible. Classical machine learning has millions and billions of parameters in their model that they optimize. And it's only possible because of this trick that I said earlier, that they never really have to run, if they've got 1 million parameters, they don't have to run 1 million computations to get the derivative. They can actually share information so that they're in sublinear time in the number of parameters. So in this sense, we're actually not doing too well at the moment.
And you need to run 2, you need to evaluate the circuit, for each parameter, you need to evaluate 2 circuits, which is thousands of shots. But then you need to do that every single step of the algorithm, right?
Yes, so exactly. So
you then take a step in gradient, and then you need to do the same thing again.
Yeah, exactly. Okay. So unless we have queuing problems and overhead, in some sense this is really quick. But you're right. In the end, we want to build models with a lot of parameters, and optimization involves a lot of steps. So we're talking here about millions and millions of circuit evaluations, and the technology has to match that. That's for it to enable quantum machine learning.
And just one last thing, can you use this method on some sort of black box where you have an input which gives you an expectation value output, and you don't know the structure of the circuit inside?
Yeah, no, you have to even know what gate you're updating at the moment, because so for example, so what's the story here is that if your gate is again generated by encoding your parameter in the time evolution of some Hamiltonian, so the gates that we were looking at earlier, then if the Hamiltonian has a spectrum of 2 distinct eigenvalues, then you can use these 2 times parameter shift rules. If you get more complicated structures, you might still be able to have, like, for example, 4-step parameter shift rules or 4-term parameter shift rules. But we also try to do this for continuous variable, quantum gates, where you've got like an infinite spectrum. And there's some gates it works and some gates it doesn't. So you really have to know what is in the black box. But in Penny Lane, for example, you can optimize any circuit, because if Penny Lane encounters a gate where we don't have a parameter shift rule, it literally just goes back to finite differences, and then it approximates the gradient, which, yeah, if your noise is not too big, also works fairly well. Especially on simulators, obviously, it works very well.
Okay, great, thank you.
Okay, I don't see any urgent. Federico. Okay, go ahead.
Hello, can you hear me?
Hey.
Yes, so one first remark regarding the point that Alistair was raising, having to take all these gradients. Does it make sense for these type of computations to do, now I forget what it stands for, but I think it's called SPSA, where essentially you choose randomly one of the gradients to evaluate, and you follow it down, and then this should converge also.
Yeah. Totally. So actually, we were just busy adding this to Penny Lane, for example, and so as part of like this is really, so I wonder if there's probably a paper that also proposed this, but like almost any optimization method you see in machine learning has kind of been proposed to have a quantum equivalent in some sorts, and and the point, or the nice point is, sorry, I'm jumping like forth and back, but if I go to this like initial slide of the example here, really you can use anything that machine learning has in terms of optimization, as long as you know what the gradients are, because machine learning is in 99% of the cases is based on, of training models is 99% of the cases based on gradient-based optimization. But you can just plug in anything that you have in classical machine learning, as long as you can get what the optimizer needs out of your quantum circuit.
Sure. And another question is just maybe to understand the context better, is so in this case you've shown the quantum model to be a circuit. So one thinks of, so for example, you were saying these VQE or these NISQ algorithms, where really one would tune the parameters of the gates in the algorithm.
Yeah.
You were mentioning also something like initialization, or is there other areas where you see this machine learning playing a role for the whole quantum computing paradigm?
Do you mean now where machine learning can inform how we build quantum computers, or do you mean like in terms of like how we pick a quantum computation to do good machine learning?
I think both to some extent. I mean,
no, I think so. Both questions are super important. Like the one, so why I haven't spoken about, maybe lots of people who give quantum machine learning talks would now say this is my favorite ansatz and this and that, but I'm always very critical about these. So we don't know which type of quantum circuit ansatz is really powerful. Why don't we know that? Because it's actually quite hard to ask that question scientifically sound. Why? Because in classical machine learning, to say my model is good or better than another model, you just run experiments on very big data sets and then you show what's the result. Does it learn or not? The experiments we can run are very small. On hardware, they're very noisy. On simulators, like you can't scale them. So we can only answer these questions for very small data sets in the first place. But secondly, also, it's not so clear. So if we start thinking about theory, can we say theoretically this is good or not? The question of how to show that something generalizes well is actually really hard. So even in classical machine learning, people have beautiful theories about it, but only for very small subsets of problems. So this is, in other words, it's a beautiful research field, but it's extremely challenging to say something about which circuit is actually better for machine learning. And it depends so much on your problem as well. But we're at it, like more and more papers coming out about this. Can machine learning influence quantum computing? I think very much. And I think the way forward is this idea of differentiable programming. I think quantum computing really has to and does think of itself in this new framework of making, making the control parameters accessible to the user. Because, so at the moment, we, for example, so let's put it like that. If people from quantum control build a quantum computer, they have to get a headache about how do they get a Pauli X rotation nicely and implemented. And sometimes they have to tweak things and change their parameters and whatever. But in this sense, I don't really care if I've got a Pauli X rotation. I just care that I've got some kind of quantum computation that has some kind of parameters, which might be a lot more efficient than like going through like, you know, the route of like having to compile, having to do all these things. So I think we can add a layer to quantum computing where, okay, give me your control parameters and I optimize. And I tell you what model you can like do with this. So I think this is super interesting for people who develop quantum computers as well.
Thank you.
Okay, I also have a couple of questions, but I think in order not to make the break even shorter, I will ask them in the breakout room, and everybody who's interested can follow to this room. And with this, I would like to thank both Maria and Ross for their very engaging talks this morning. Enjoy your coffee break, and let's continue the discussion in the breakout room.
Okay, just a quick drop quickly. The main room will be the one dedicated to the speakers because one of the speakers has a client that doesn't support breakout session. And so those who didn't write me before are assigned immediately to the off topic. If you want to come to another room, you will have to quit. And the session starts in now.
Okay, so then let me follow up immediately. Maria,